Yeah, welcome now. Then coming to water distribution, there is no much numericals to remember except that Hardy-Cross equation. Head loss is equal to K times Q power X. Right, this equation you have to remember. Then in addition to that, right, what else you need to remember is in any closed pipe network system, two hydraulic conditions are there. So any pipe network, any balanced pipe network carrying correct flow rates has to satisfy the following conditions. Based on those two conditions, he is asking questions in exam. One is, at any pipe junction, flow in at pipe junction is equal to flow out. Junction means two or more meeting point is called as a junction. At any pipe junction, flow towards junction is equal to flow away from the junction. Flow in is equal to flow out. Or otherwise you can write sigma q in is equal to sigma q out. So based on this he is asking questions. And second condition is algebraic sum of head losses around a closed loop must be 0. Around a closed loop must be 0. That is sigma h around a loop must be 0. So based on these two conditions, he is keep on asking questions in GATE exam. And coupled with this question, equation, Hardy-Cross equation. Okay. Hardy-Cross equation for head loss. Based on this, he is asking numericals in GATE exam. Beyond that, nothing is there to remember in water distribution. Okay. So this is about water supply engineering. So whatever I taught earlier, equations, and these few equations, if you remember, more than sufficient. Network will be given. Some missing data in a network you are expected to find out either using sigma flow in is equal to sigma flow out equation or algebraic sum of head loss around a closed loop must be 0. That's all. Coming to wastewater engineering. the first topic is estimation of dry weather flow and wet weather flow. So dry weather flow is equal to, it is population into, first numerical I am talking, it is per capita water supply into factor. Right? And Q, this factor is normally given to you. This is a fraction of water supply converted into sewage. Water supply converted into sewage. So normally its value is 0.7 to 0.8. It will give you 75% means 0.75, 0.70% means 0.7, 80% means 0.8, something like that. Per capita water supply, that will be given, population is given to you. Then wet weather flow we work out by using equation air by 360. In this A is equal to area of catchment, I is equal to impermeability factor, which we can work out by using A1 I1 plus A2 I2. The catchment having different surfaces, having different I values, we work out by using this equation AN IN by total area. Okay, sigma AI into II by area, that will give I value, and R value we work out by using equation 25.4A by TC plus B. So in this, A and B are constants whose value depends on duration of storm. Storm duration T. So for storms of duration 5 minutes to 20 minutes, we take A value is equal to 30 and B value is equal to 10. For storms of duration greater than 20 minutes, A value is taken as 40 and B value is taken as 20. Okay? Then one more thing in that equation is TC. TC stands for, I'll repeat once again. So up to chlorination we discussed before before lunch break. After that miscellaneous treatment, there is no much numericals. Then straight away water distribution. Water distribution only that hydraulic conditions. Based on that hydraulic conditions, they may ask some questions. Condition 1 is, at any pipe junction flow in must be equal to flow out, or Q in is equal to Q out, and algebraic sum of head losses around a closed loop must be 0. So based on this, they are asking questions numericals in GATE exam. In water distribution, nothing is there beyond that. Then coming to wastewater, first topic is working out dry weather flow and wet weather flow. Where dry weather flow estimation is so simple and so easy. Nothing is there. It is population into per capita sewage flow into per capita sewage flow. Per capita sewage flow is nothing but per capita water supply into factor. And wet weather flow we estimate by using rational formula. This formula is called rational formula. It is an empirical formula. Using the same formula we can work out the things. Then in that formula, A is equal to area of catchment in hectares. Catchment area in hectares. You have to substitute because that is a empirical formula. This will get mm per hour. Then if you substitute Q value, you will get straight away in meter cube per second. Okay. So in this equation, TC is known as time of concentration. So time of concentration is function of catchment factor and as well as drain factor. Time of concentration. So in minutes, normally we work out this in minutes. Time of concentration in minutes is equal to this time of entry plus time of flow, where T is known as time of entry. in minutes. TF is known as time of flow in minutes. Time of entry plus time of flow. Okay? TC you can calculate. So if T is not given, if duration of storm T is not given, then T is taken as equal to TC. That point also have to remember. Okay? So T is equal to TC you can take. Duration of storm is not given. Because rational formula is true for condition for storms whose duration is greater than or equal to time of concentration. Okay, minimum condition we take. So whenever T is not given, we comfortably take T is equal to time of concentration. T is equal to time of concentration, and which is also taken as duration of storm. Then when storm duration is greater than or equal to time of concentration, then only it produces maximum discharge. So Q wet weather flow we get maximum value. Okay. Then coming to design of sieverts. So sieverts are designed based on two things. One is to work out diameter of siever and slope of siever. Diameter D, slope S. So two unknowns are there here. So we use two equations. One equation is continuity equation, right? This is coupled with Manning's formula. First we work out velocity of flow by using Manning's formula. V is equal to 1 by N R power 2 by 3 into S power half. In this equation, N is known as Manning's constant. Manning's rugosity constant. R is equal to hydraulic mean radius wetted area by wetted perimeter. S is equal to slope of hydraulic gradient line, nothing but bed slope of siever. Okay? Slope of siever this is. So, this is equation 1. This is coupled with the Q equation. Q is equal to area into velocity. So by solving these 1 and 2 equations, we can find out diameter of the siever, slope of the siever. Okay? By solving 1 and 2, we can find out diameter of the siever and slope of the siever design. But the thing is, sievers always run with partial flow conditions. When they run with partial flow conditions, finding that hydraulic mean radius and wetted area is not that easy. So we have got some simplified procedures to work out these things. For siever running full, so R is equal to A by P, we take it as D by 4, and wetted area is equal to pi by 4 D square. For siever running half full, condition, R is equal to still A by P, which is equal to D by 4, but area is equal to pi by 8 D square. So for siever running full, running half full, these are the parameters R and A. So for siever running full, running half full, velocities are same, but discharges are not same. Therefore carefully we need to work out. But sievers running more than half full, less than half full, we work out the things by using sievers running less than half full and more than half full. Hydraulic flow parameters are read from partial flow diagrams. Partial flow diagram or partial flow table. That's a point you have to remember. Okay? This is the note. Sewer running full, more than half full, less than half full. Partial flow diagram or partial flow table is used to find out this hydraulic flow parameters. So partial flow diagram you see, table this is. Here we will find d by d, for a given d by d, we find q by q, v by v, a by a, etc. Something like this. Okay? Or same thing will be given in the form of many parameters, in the form of diagrams also. In the form of diagram also they may give. So here you will give d by d, in this axis you will give q by q, v by v, a by a, etc. So for everything they will give you a diagram like this. Discharge diagram, velocity diagram like that, area diagram. So from there we can pick up the values. So this small d, small q, small v, small a are partial flow parameters for sewer running, partial flow condition. Capital D, capital Q, capital V, capital A represent flow parameters for sewer running full. So small d, small q, small v, small a. In this d is equal to depth of flow and capital D is equal to diameter of sewer. So in this equation, small q, small v, small a, etc. are flow parameters for partial flow conditions. Capital Q, capital V, capital A, etc. are flow parameters for full flow. Sewer flowing full. Full flow it is easy to work out. So by knowing the full flow, we work out for partial flow. Okay. So with the help of d by d, then we try to work out this q by q, v by v, a by a values. From there we try to find out. That's all. That much idea is there, more than sufficient to work out numericals in case of sewer design. And one more thing is, this flow velocity should be, so self-cleansing velocity should be less than flow velocity provided in the sewer. That should be less than non-scouring velocity. Flow velocity should not be more than self-cleansing, should not be less than non-scouring. Okay? So self-cleansing velocity sometimes we work out by using expression 8k by f into s minus 1 gd. This equation also very useful while working out problems. When they ask you to work out self-cleansing velocity, we work out using this formula. So flow velocity that we provide in the sewer should be more than self-cleansing velocity and it should be less than non-scouring velocity. Understood? For which we need to design the sewer. Okay. Next coming to next topic, characteristics of sewage topic. The first thing is how to work out these BOD problems. So 5-day BOD at 20 degrees Celsius at a temperature 20 degrees Celsius. We denote it by, in the laboratory we work out by measuring initial DO and final DO. This is to be multiplied with the dilution factor, where DF is equal to, it is 300 by Vs or 100 by percentage sewage sample tested or percentage dilution. You can also write it as percentage dilution. How much diluted? 2% dilution or 3% dilution, something like that. Okay, this is laboratory model. 5-day BOD at 20 degrees Celsius. We measure BOD value. So dy is dy initial, dyf is dy final. Dy is dy initial, dy. Dyf is final dy. Final dy after 5-day incubation. Final dy after 5 days incubation at temperature 20 degrees Celsius. And sometimes dy initial may not be given. Dy initial we work out. Dy initial is nothing but dy mix. Two different samples having two different values. V volume of distilled water with a DO, DOD mixed with a Vs amount of sewage sample with a DO, DOS. And after mixing both of them together represent a DO mix. Then DO initial is nothing but DO mix. Sometimes we are expected to work out DO mix also. Okay, and you can work out BOD at any temperature at any time. BOD at any temperature T degrees Celsius and at any time T days. We can work out this by using one mathematical expression. We denote it by YT at T degrees Celsius. So BOD at any time, at any temperature is equal to, right? It is L0 into 1 minus e power minus kt into T. Using this expression you can work out BOD at any time and any temperature. To find out that constants L0 and kt, you require one laboratory data. Therefore, this is equated to 5-day BOD at 20 degrees Celsius. So this is equated to dy initial minus dy final into dilution factor, which is also equal to 1 minus, L0 into 1 minus e power minus kt. Kt means k20 into 5. So from this, by equating this, we can find out L0 value and k20 value. This k20 value we work out for base E. Okay. So K at any temperature, kt is known as BOD rate constant, whose value depends on temperature T. So K at any temperature is equal to, it is K20 into 1.047 into T minus 20. So once you know K20 value and L0, and you can work out K at any temperature, then you can find out BOD at any temperature at any time. Just L0 and K, T values are known to you. Just by substituting in this equation you can find out. Okay. So this is how they ask questions. Then in addition to this, one more thing that we try to work out is BOD remaining at any time T. BOD remaining at any time T. That is LT is equal to, it is L0 into e power minus K into T. It also depends on temperature. K value depends on temperature. Okay. BOD remaining at any time T also equal to organic matter remaining at any time T, which is also equal to organic matter remaining at any time T. Both of them are same. Okay. So use value also depends on K value depends on the same K. So two expressions we have. One is Yt at any temperature is L0 into e power minus Kt into T. Second one is Lt is equal to L0 into e power minus Kt into T. So two equations are there. So one is to measure BOD, other one is to measure BOD removed. This is BOD removed. This is BOD remained. That is organic matter removed. This is organic matter remained. Okay. Two expressions. Using this, you can any problem you can work out with the help of these expressions. Okay. In addition to that, one more concept in BOD topic is population equivalent. This population equivalent is equal to, it is total BOD by per capita BOD. So total BOD is Q into Y by per capita BOD. Population equivalent of any waste. Therefore, total BOD of any waste we can also work out by it is Q into Y, which is also equal to population into per capita BOD. So, very useful expression this also. Per capita BOD is a constant. So, for a given total BOD, you are expected to find out population equivalent. For a given population, you are expected to find out total BOD. Okay. So, COD, there is nothing is there, only definition. And relation between BOD and COD is always greater than or equal to BOD. BOD represent only oxygen demand of biodegradable organic matter. Only represent oxygen demand of biodegrades in sewage, whereas COD represent oxygen demand of both biodegrades and non-biodegrades in sewage. Non-biodegrades in sewage. Okay. So generally, biodegradable organic matter present in sewage, both you can find BOD and as well as COD. But sometimes non-biodegrades also present. Definitely, non-biodegradable organic matter present. Definitely COD is much more than BOD. If non-biodegradable organic matter is not there in sewage, then COD and BOD are same. Then one more is critical oxygen demand. Critical oxygen demand we estimate by chemical formula. Estimated with the help of chemical equation given in the question. Okay? That much idea is there more than sufficient. And coming to cyclable solids. Cyclable solids present in sewage, they are measured by using Imhoff cone. Cyclable solids in sewage measured by Imhoff cone. Measured by Imhoff cone test. Imhoff cone test, you will find a cone like this. It's a graduated cone, it is cylindrical cone. So we keep 1 liter, we pour 1 liter sewage sample. Okay. Then what happens? After half an hour, right, all the solids present there, accumulated bottom, upper bottom, the solids present. Solids accumulated at bottom. They are called cyclable solids. Cyclable solids accumulated at bottom is this much. So that's how we can find out. Okay? This is called Imhoff cone. Imhoff cone. Next. And coming to wastewater treatment. So wastewater treatment we can categorize into 4 classes. Domestic wastewater treated in stages. One is preliminary treatment. Second is primary treatment. Third is secondary treatment. Fourth is tertiary treatment. Fifth is sludge treatment. All is put together total treatment of wastewater. Tertiary treatment normally in India we don't employ. We stop at secondary treatment. For recycling and reuse of sewage is required, then people go for tertiary treatment. Just for disposal you can stop at secondary treatment just to save disposal. And you want to reuse and recycle wastewater, then tertiary treatment also given to wastewater. Okay. So preliminary and primary treatment put together. Primary treatment include preliminary treatment as well. So it includes screens, then grid chamber, then skimming tank, then primary clarifier. all these four things put together, it is known as, this is, if you stop at skimming tank, it is called preliminary treatment. If you go beyond that, you four of them together known as primary treatment. So primary treatment include preliminary treatment as well. That's a point you need to keep in your mind. We employ only these three, preliminary treatment, and if you include primary clarifier also, then it's called primary treatment. So screens are normally used for removing large floating objects. So large floating objects are removed by screens. Wastewater are removed by screens. Then grit chamber remove grit particle. Remove grit from sewage flow. And skimming tank remove oil and grease. And primary clarifier remove settleable organic solids. So each one remove one kind of contaminant present in sewage. Generally, the screen design is not that important. So, very important component of primary treatment, if at all they ask any question, that is from grit chamber. So, in grit chamber, the things which you need to remember to design them are the rectangular tank. So, design is based on one, detention time, two, flow velocity. So using detention tank, what you can find out? Volume of grit chamber. So normally we provide detention time in grit chamber anywhere between 1 to 3 minutes. Okay? Volume will get, this volume is equal to L into B into H. Then using flow velocity, you can find out cross section area of grit chamber. So this cross section area is equal to, it is B into H. So then length of grit chamber you can find out by either you can use volume by cross section area or otherwise VH into detention time. This also will give same thing. So that's all. Then B is to H ratio we provide 1:1 to 5:1. Then we fix width of the grit chamber and depth of the flow in the grit chamber. That's what is called design of grit chamber. That's it. If you ask any question, that is this only. In addition to that, grit chamber, something like a sedimentation time, settling velocity of grit chamber also, settling velocity of grit particle. you can work out by using same equation if there is a laminar flow condition. Laminar flow, and you can also make use of equation for 100% removal, or you can also find out plan area or surface area of grid chamber, surface area of grid chamber. You can also work out by using same sedimentation tank design, that V0 surface loading rate or surface overflow rate are given. Then you can find out surface area. The surface area also L into B. That way also you can do it. Alternate approach this is. Okay. In addition to that, conditions for 100% removal also you can use. Conditions for 100% removal of grit. For 100% removal of grit, first condition is settling velocity of grit particle should be greater than V0. Second condition is H by Vs of the grit particle should be less than or equal to L by Vh. Then 100% removal of grit. So based on these concepts, sedimentation tank concepts also, there are framing questions in grit chamber related to grit chamber. Okay. So grit chamber, from grit chamber only they are asking more questions. Primary clarifier design is same. Skimming tank is, nothing is there to design. Primary clarifier, remove 60 to 70% settleable organic solids. Of biodegradable nature. And it also remove, indirectly we achieve 20 to 30% of BOD. Because they are biodegradable in nature, we can also partially relieve from BOD. This point they are asking in exam. And design of primary clarifier same as sedimentation tanks only. So design is based on surface loading rate or surface overflow rate V0, whose value normally taken very high, 30 to 50 meter cube per day per meter square. And second is detention time, 1.5 hours to 2 hours more than sufficient to capture them. So using surface loading rate you can find out surface area of primary clarifier. And using detention time you can find out volume. That's all. Volume by surface area will give depth. Surface area is equal to B L into B. So using L is to B ratio you can find out rest of the information. So all of them we got LBH. That's what is called design. Okay? This is how we can design primary clarifiers. So for latecomers, again, once again, we started with water distribution. So before lunch, we before lunch we completed up to disinfection. Then beyond after lunch, we start with water distribution. Then all kinds of numericals that are possible in GATE exam. So we discussed briefly. Next is secondary treatment. So the secondary treatment of wastewater we carry out by two methods. Activated sludge process. Second one is trickling filters. So in case of activated sludge process, there are so many number of design parameters. Okay. One is FIM ratio, 2 is mean cell residence time theta c, 3 is sludge volume index, 4th is volumetric loading rate or organic loading rate or BOD loading rate. 5th is organic loading rate or BOD loading rate. 5th is aeration time, aeration period. 6th is BOD removal efficiency. So this many number of parameters are there, and 7th is recycling ratio. So this many parameters are there to design activated sludge process. This many equations you have to remember. Important is first 3 are very, very important. First FIM ratio is Q into yi minus y by V into x. Substitute Q in meter cube per day, yi and ye milligram per liter, right? V in meter cube, x in milligram per liter. Then you get FIM ratio in 1 by day. So we express this. We get this value anywhere between 0.2 to 0.4 day inverse. So for exam point of view, whenever FIM is given, you are expected to find out volume of aeration tank. Volume of aeration tank is given, you are expected to find out F by m, along with other things. So for a given F by m, we work out volume of aeration tank. For a given volume, we work out F by m ratio. Q and YE are constants. Okay? That's how we frame a questions in exam. Normal ratio is 0.2 to 0.4 day inverse. The second one is mean cell residence time, theta c. We also call it as sludge age. All of them one and same only. So big equation now to remember, it is V into X by QW into XU plus Q minus QW into XE. So you have to understand this parameters. The diagram is very, very important. What is the diagram? This diagram. This is aeration tank followed by secondary clarifier, okay. In aeration tank we supply the wastewater passing through aeration tank, then it is put into secondary clarifier. So Q amount of wastewater with influent BODY applied into V volume of aeration tank with concentration of microorganisms in aeration tank is X. Out of that, QE effluent is disposed of containing YE amount of BOD and XE amount of organisms. This effluent will go to disposal. This effluent to disposal. This influent applied. Influent we apply here. Q amount of influent with YE BOD. Volume of aeration tank. X is MLSS in aeration tank. Mixed liquor, suspended solids are nothing but microorganisms. So these microorganisms, they settle down here. Portion of the microorganisms settle down, taken back to process, recycled here. Okay. So we get QW. Q amount of underflow with concentration of organisms is XU. Out of that, QR amount is recycled with concentration XU. Remaining QW amount will go to treatment. This is waste to sludge to disposal. Treatment. The waste to sludge to treatment. So this diagram is understand, then you can get all those things. Based on this diagram only, everything depends. This is sludge. Settled at bottom. So in this X is MLSS concentration, MLSS in wastewater flow. So based on this diagram only, all those parameters we can work out. So this is very, very important. Mean cell residence time and F by M ratio. These two are very popular questions in competitive exams. So to work out this mean cell residence time, the unit system that we follow. So mean cell residence time, theta c is equal to, it is V into X. Substitute V in meter cube, X in milligram per liter. Mixed liquor, suspended solids means solids only. Solids are expressed in milligram per liter. This QW into XU plus Q minus QW into XE. So this QW we substitute in meter cube per day, XE in milligram per liter. Similarly here also Qs we substitute in right meter cube per day, and X values we substitute in milligram per liter. So milligram liter will go off, meter cube will go off, you are left with days. So you will get days. So mean cell residence time, normally we provide 4 to 15 days. So from this you can also work out mass of solids wasted per day, which is nothing but QW into XU plus Q minus QW into XE. Anyway that is not given means, then you can take it as Vx by theta c. This is also you can find out. Either this information is there, you can use this information to work out. Otherwise Vx by theta c also you can use and work out mass of solids wasted per day. So two parameters in this equation you can take 0 if required. One is YE and XE. If YE and XE are not given, YE and XE are not given, if required, they can be taken as 0. Okay? That point also you have to remember. Activated sludge process is very, very important. First two parameters are very, very important. Okay. Next important parameter is sludge volume index. The sludge volume index is worked out by definition. Okay. It is space occupied in ml by one gram of MLSS after settling for 30 minutes. In 1 liter sewage sample, is known as sludge volume index. Okay, we work out sludge volume index by space occupied by X. X is MLSS only. Space occupied you substitute in grams. This in space occupied we substitute in ml, and X value we substitute in grams. So its unit is ml per gram. And one more parameter is sludge density index. So in GATE exam one time this question also asked. Sludge density index. So it is sludge volume index per 100 ml is known as sludge density index. So sludge density index is equal to sludge volume index by 100. Oh sorry, 100 by sludge volume index. Then you will get this answer gram per 100 ml. The unit of this is gram per 100 ml. If you take inverse of sludge volume index, It is gram per 1 ml. Sludge density index is expressed gram per 100 ml. Okay. So therefore, by 100 by sludge volume index will give sludge density index. Okay. This question also asked in GATE exam. Next parameter in activated sludge process is volumetric loading rate or organic loading rate. We will also call it as organic loading rate or BOD loading rate. So volumetric loading rate is equal to this total BOD applied by volume of aeration tank. So this will give volumetric loading rate. Substitute Q value in MLD, YI value in milligram per liter, so that this product will give answer in kilogram per day by meter cube. So we get kilogram per day per meter cube. The unit of volumetric loading rate is, it is normally 0.3 to 0.6 kilogram per meter cube per day or kilogram per day per meter cube. This is another parameter, fourth parameter. Fifth parameter is first three are important for aeration period. So this aeration period is nothing but detention time. We don't call it as detention time, technically it is known as aeration period. So aeration period is equal to the volume of aeration tank by flow rate. So substitute this in meter cube, this in meter cube per hour, straight will get answer in hours. So normally we provide aeration period anywhere between 4 to 8 hours. Okay? For activated sludge process, aeration period is 4 to. How long oxygen is supplied to microorganisms? That's called aeration period. As long as wastewater present in aeration tank, that much time period oxygen is supplied. How long wastewater remain in that tank? Detention time that we provide. So this is nothing but detention time only. Understood? Next parameter, BOD removal efficiency. So efficiency of BOD removed is BOD removed by BOD applied into 100. BOD removed is YI minus YE. BOD applied is YI, influent BOD. YI is called influent BOD. YE is called effluent BOD. So BOD removed by BOD applied. YI is influent BOD. YE is effluent BOD. So YI minus YE by YI into 100. That is efficiency. Seventh question. What is seventh one? Recycling ratio. This is QR by Q. So this QR by Q is given as X by XU minus X. X by XU minus X. So from this you can also work out QR. So normally this QR by Q ratio we provide anywhere between 0.25 to 0.5. To get this QR by Q ratio 0.25 to 0.5, we have to maintain X concentration in aeration tank as 1500 to 3000 milligram per liter and XU concentration 9000 to 12,000 milligram per liter. This and all you need not remember. Okay? And XU you can also work out by using 10 power 6 by sludge volume index. Our sludge volume index XU straight will get in milligram per liter. As it is work out. Okay, using sludge volume index, you can also work out sludge volume index by using 10 power 6 by xc. This will get gram per ml, ml per gram. Okay, that way also you can do it. Sludge volume index. So these are the equations which you need to remember. If it is what do you call activated sludge process system, you want to design that system, these are the number of equations, so many you have to remember. This many numbers are there. Sometimes aerator capacity also they will ask. So total oxygen supplied by capacity of each aerator will give number of aerators required, something like that. That much depth is not, will not go. Next is trickling filters. Okay. Trickling filters, what is expected is design of trickling filter. Trickling filter design is based on NRC equation. NRC of USA equation. National Research Council of United States of America equation. So they have given BO removal efficiency of trickling filter is equal to hundred by 1 plus 0.0044 root of Q into Y by V into F. So this equation is given. This equation, how to make use of this equation to design the system. So in this equation, Q into Y by V is known as organic loading rate or BOD loading rate. Because it is empirical equation, so units must be properly substituted. It is kilograms per hectometer per day. It should be in this unit system, organic loading rate or BOD loading rate. So if we take only Q into YA, what is that? Total BOD applied to trickling filter. Applied to trickling filter in kilogram per day. How to get this in kilogram per day? Substitute Q in MLD and YI in milligram per liter. then automatically this product will give answer in kilogram per day. Understood? And V is known as volume of trickling filter. Which unit system it is there? Hectometer. Hectometer is unit for volume. So then you can convert hectometer into meter cube. 1 hectometer is equal to 10 power 4 meter cube. Hectares is unit for area, area into depth, volume. This is area, this is depth. Area expressed in hectares, depth expressed in meters. So hectometer is unit for volume. So you can convert that into meter cube into hectometer also you can convert, vice versa. So once you know volume of trickling filter, we assume depth of trickling filter. Depth of trickling filter we provide anywhere between 0.9 meters to 2.5 meters, right? Then you can find out surface area of trickling filter. This is equal to pi by 4 d square, which is equal to volume by depth. Then from this you can find out diameter of trickling filter. D you can find. That's all. That is what is called design of trickling filter. And very important thing in this equation is F value. F is known as recirculation factor. So this F value we work out by using equation 1 plus R by I by 1 plus 0.1 R by I whole square. So from this equation you can find out F. In this equation R by I is known as recirculation ratio. So this, which is nothing but effluent recycled to influent applied. Effluent recycled back to process. Amount of effluent recycled or flow rate of effluent recycled back to process by flow rate of influent applied. That is taken as R by I. Okay. So based on this F value, trickling filters are classified into two categories. One is standard rate trickling filters. For standard rate trickling filters, right, there is no recirculation. R value is equal to 0. If R value is equal to 0, R by I is equal to 0, then F is equal to 1. For high rate trickling filter, R value is not equal to 0, R value is greater than 0, R by I is greater than 0, then F is greater than 1 will get. Okay? So that's the difference between high rate and standard. Standard rate trickling filter, no recirculation. No recirculation of effluent. There is a recirculation of effluent. High rate trickling filter only recirculation. There is no recirculation in standard rate trickling filter. That point you have to remember. Okay. This is about trickling filters. So after trickling filters, then we move to sludge treatment. Okay. In structure treatment, first thing is how to work out specific gravity of sludge. Specific gravity of sludge is equal to 100 by specific gravity of solids plus, how to work out specific gravity of sludge. Sludge is heterogeneous mixture of two things, solids and water. Sludge is a mixture of two things. One is solids, the other one is water. Again solids, there are two types of solids in sludge, volatile solids and non-volatile solids. We write shortcut VS. This is non-volatile solids. Okay? So you want to find out specific gravity of sludge, right? You need to know first specific gravity of solids. Finding specific gravity of sludge itself is a popular question in GATE exam. So specific gravity of sludge is equal to, it is worked out by first working out specific gravity of solids. So solids is a mixture of two things. 100 by specific gravity of solids is equal to percentage volatile solids by specific gravity of volatile solids plus percentage non-volatile solids present in sludge by specific gravity of non. If you get this, then you can work out specific gravity of sludge. 100 by specific gravity of sludge is equal to this percentage solids in sludge by specific gravity of solids plus percentage moisture content of sludge by, moisture content is nothing but water content, specific gravity of water. So this is how we can work out specific gravity of sludge. To work it out, we require specific gravity of solids. If given, well and good, otherwise we work out. We will give you percentage volatiles and specific gravity of volatiles, percentage non-volatiles and specific gravity of volatiles. Why to work out specific gravity of sludge? The specific gravity of sludge is worked out to work out density of sludge. Then density of sludge is equal to mass density of sludge. It is specific gravity of sludge into density of water. So density of sludge is equal to nothing but mass of sludge by volume of sludge. So from this what you can find out? Volume of sludge you can find out. So volume of sludge is equal to, it is mass of sludge by density of sludge. Okay, that's how we can work out. So all those things are linked here. So you have to find out this mass of sludge and volume of sludge. This mass of sludge is equal to mass or weight of sludge produced per day is equal to, it is 100 by 100 minus P into M, kilograms is produced every day. The mass or weight of sludge produced. And volume of sludge produced is equal to, the mass of sludge produced per day by density of sludge. Therefore it is 100 by 100 minus P into M by rho sludge. Straight will get in meter cube. This is. That will get kilogram, this will get in meter cube. Meter cube per day, like that you have to read. That's how you can work out. So in both of the cases M you have to find out. This M is equal to mass of dry solids in sludge. Mass of dry solids in sludge in kilograms per day. So this M value you can work out by using equation Q into efficiency of sedimentation tank into Cn. This efficiency of sedimentation tank into Cn is nothing but Cn minus C out. Cn minus C out represent concentration of dry solids in sludge. That's how we can find out M value. So substitute Q in mLD and concentration in milligram per liter. Then you will get that M value in kilogram per day. Understood? This we work out in kilogram per day. mLD into milligram per liter will go kilogram per day. So only M, where P is equal to moisture content of the sludge. Percentage moisture content of the sludge. How much moisture is there in the sludge? P is equal to percentage moisture content of sludge. Moisture content of sludge given in percentage. Okay? That's all. This single formula based on this left and right is asking question. So if you simplify this question, you can find out volume of sludge before treatment, volume of sludge after treatment. After treatment, volume decreases. It is 100 minus P1 by 100 minus P2 into V1. So V1 is equal to volume of sludge before treatment, P2 is equal to volume of sludge after reducing moisture content after treatment. Okay? So volume reduction takes place. P2 is equal to percentage moisture content of treated sludge. So before treatment, raw sludge, moisture content of raw sludge. After treatment, is the moisture content of treated sludge. And P1, okay, P1 is equal to percentage moisture content of raw sludge, untreated sludge or fresh sludge. And P2 is equal to percentage moisture content of digested sludge or treated sludge. Raw sludge or fresh sludge. That means before treatment. This is after treatment. This is before treatment, moisture content is P1. After sludge treatment, moisture content is P2. Understood? Okay. So based on this, he is asking questions in GATE exam. Then after this, we are expected to design the sludge digester. Design of sludge digester. Sludge digester is designed based on formula. That is capacity of sludge digester. Capacity nothing but volume of sludge digester is equal to, it is Vf plus Vd by 2 into T. So Vf is equal to volume of fresh sludge produced per day, right, which is nothing but V1 only. Vd is nothing but volume of digested sludge produced per day, nothing but V2. So fresh sludge has got moisture content P1, digested sludge has got moisture content P2. From that you can work out Vf and Vd, and this T is known as digestion period. Digestion period in days this is. So this T value normally range anywhere between 30 to 60 days. So based on temperature we decide. So anaerobic system it takes its own time. This is capacity of sludge digester. That is what fixing that capacity is known as design. Clear now? That's all. You can't get anything more than this in sludge treatment. Next move to septic tanks. Septic tanks also same as a sludge treatment system only. So here we'll fix the capacity of septic tank. Oh, I forgotten here. Okay. So once you find V, 1 minute. The next step is we assume the depth of sludge digester anywhere between 6 meters to 12 meters. Then you can find out surface area of the sludge digester. Or plan area of sludge digester, which is equal to pi by 4 d square, which is equal to volume by depth. Then from this you can find out diameter of sludge digester. That is complete design. That's all. Okay. Now let us go ahead with the septic tanks. And of course rate of gas production also they are asking. Rate of gas production at sludge treatment is, normally it is 0.9 cubic meter for every kilogram of volatiles destroyed. Okay, so in that term, again they are asking how much amount of methane gas is produced. So out of total gas produced, methane gas is 60% to 70%. Carbon dioxide gas is, right, 20 to 30%. Remaining gas are in traces. Carbon dioxide is 20% to 30% gas. And remaining gas, H2S, is in small amount, trace. Hydrogen sulfide is very small amount, I am not writing there. So energy content also they are asking. So energy content of methane gas is, energy content of methane gas is equal to, it is 5200 to 5800 kilocalories for every meter cube of methane gas. 1 meter cube of methane gas contain how much amount of energy? 5200 to 5800 kilocalories of energy. So therefore it is used as a fuel. So all these they are asking in exam. Okay. Next let us see septic tanks. Septic tank also, we fix up the capacity of septic tank. Capacity means volume of septic tank. It is also anaerobic system. V is equal to, it is volume of settling zone plus volume of sludge zone. V is nothing but volume of settling zone of septic tank. So the settling zone of septic tank will be fixed by detention time. Q into detention time. Q is equal to number of users, right, into per capita sewage flow or per capita water supply into factor. And dt is known as detention time. Normally we provide, it is anywhere between 24 hours to 48 hours. That is 1 to 2 days detention time we provide. So from this we get volume of settling zone. And sludge zone of septic tank is fixed based on rate of sludge production into number of users into cleaning period. RSP stands for rate of sludge production. So as per IS code, this rate of sludge production normally vary anywhere between 30 to 40 liters per person per year. Cleaning period is normally we provide 1 to 3 years. Cleaning period, or is also known as desludging period. It is 1 to 3 years. Once in 1 to 3 years, septic tank is cleaned or sludge is removed from septic tank. Okay. So then both of them are known. Then you can find out total volume of septic tank. So once you know the volume of septic tank, then you can find out surface area or plan area. Plan area of septic tank is equal to, it is volume of septic tank by depth of septic tank, or you can find out volume of settling zone by depth of settling zone or liquid depth. So plan area or surface area of septic tank is equal to, it is length into width. Usually provide length to width ratio. Based on length to width ratio, you can find out length of the septic tank and as well as width of the septic tank. That's how we can work out. So this edge settling is nothing but depth of settling zone is also called liquid depth, and capital H is depth of septic tank. Okay. L and B are length and width of septic tank. This is a rectangular tank, septic tank. L is length of septic tank and B is width of septic tank. That's it. Okay. From here only they will ask questions. So sometimes cleaning period is unknown, sometimes the sludge volume is unknown, V sludge is unknown, volume of sludge zone, volume of settling zone. Something you will give unknown, then you are expected to work out. Then after septic tanks, then we move on to oxidation ponds. So oxidation pond designs only they will ask. Design of an oxidation pond. So oxidation pond design is made by using organic loading rate or BOD loading rate. So plan area or surface area of oxidation pond is equal to this Q into Y by organic loading rate applied to the pond or BOD loading rate applied to the pond. So Q into YI is nothing but total BOD applied to the pond. Pond in kilograms per day. Organic loading rate or BOD loading rate. This value depends on latitude of a place. Based on temperature, the average temperature the place receive, we decide organic loading rate. Or BOD loading rate is expressed in kilograms per hectare per day. Therefore, what you get surface area in hectares will get. So therefore, what you get L into B value is equal to this Q into Y by organic loading rate will get in so and so hectares. Then you can convert it to meter square using L is to B ratio. Normally we provide 4:1. From this you can find out length of the oxidation pond and width of the oxidation pond. And second parameter is detention time. Using detention time you can find out volume of oxidation pond. Volume of an oxidation pond is equal to this Q into detention time. Normally detention time varies anywhere between 2 weeks to 6 weeks, or otherwise will give you in days 10 to 50 days. Okay, or approximately you can find out detention time dt or t is equal to, it is 1 by k into ln yi by ye form, where k is equal to pond rate constant in days. So therefore straight will get answer in days. 1 by day, the unit, k value, day inverse. So we will get answer in days straight away. So once you know volume, this volume is equal to what? L into B into H. Therefore depth of pond required is equal to depth of an oxidation pond is equal to, so volume by surface area. That's all. That's what is known as design of oxidation pond. Simple only. Concepts are simple just by hydraulic design most of the times. Only in wastewater engineering, slightly organic loading rate, BOD loading rate also get into picture. Okay. Next topic is disposal, effluent disposal. Effluent disposal, one popular question is working out disposal of effluents are made by either water disposal or land disposal. Water disposal is called disposal by dilution. In disposal by dilution, one popular question is disposal by dilution. Finding the concentration of the mix. This is a river. Disposal by dilution means what? Disposing effluent into water course. Disposing effluents means treated waste into river. So this is a wastewater. Effluent means wastewater only. So this is wastewater effluent. We are disposing into this river. Assuming this is a river. You have city producing waste. That waste you are disposing into this river. After treatment, of course. So this is upstream side of the river. This is downstream side of the river. So river flowing from upstream to downstream. So you are disposing wastewater effluent. Effluent means treated wastewater. How much amount? QW amount with concentration of pollutant is CW. Into river, upstream side its concentration is pollutant concentration is CR. Normally it is close to zero or little. Anybody on the upstream side further dispose, little you will find. So after mixing these two things into the water course, then what happens? This becomes C mix. Okay? Exactly at the place where we dispose, concentration is C mix on the downstream side. Further it travel onto downstream side of the river, right? Some distance it traveled in kilometers. Suppose L kilometers it travel. At L kilometers point, what is the concentration of that pollutant? You are expected to calculate. That question they are asking in GATE exam. So that concentration of pollutant there is CT. What is that CT? So two things, C mix you have to find out, then CT. This is one popular question in GATE exam. So that C mix value you can work out by using equation QR into CR, mix formula QW into CW by QR plus QW, mix formula. Mass flow in is equal to mass flow out. Mass flow, how much? What is flowing downstream side? QR plus QW flowing on downstream side. With concentration C mix. Okay, QR and QW that is flowing on the downstream side with concentration how much? C mix. It is flowing on downstream side. So therefore mass in is equal to in here. QR CR plus QW CW. Mass out is equal to C mix into QR plus QW. So therefore I am looking for C mix, I will get that C mix. So base C could be any parameter. It could be BOD or it could be DO or it could be chlorides or it could be temperature or any parameter it could be. Okay? Downstream side. So once that pollutant concentration attains C mix, when further it travel on the downstream side, its concentration becomes CT. That CT is equal to, it exponentially decreases due to self-purification capacity at a rate K in time T. So therefore concentration of that pollutant on the downstream side, the CT is equal to concentration of pollutant on the downstream of disposal. Downstream of disposal at a distance L kilometers. At a distance L kilometers. Then how to get the T value? This T value is equal to distance traveled by velocity of flow on the downstream side. Distance traveled is how much? L. Velocity of flow is V. Velocity of flow is what? Which is nothing but velocity of flow. Q is equal to area into velocity. Velocity is equal to Q by area. So it is Q by area. What is Q? Q mix. This is Q mix. Q mix by A. Downstream side this Q mix it is. I will take it as Q mix. This is nothing but Q mix. A is cross section area of river. Cross section area of river is A. Cross section area into length is equal to volume. So it is cross section area of river into length by Q mix will give T. That T you substitute in this equation, you can find out concentration of pollutant at L kilometers distance on the downstream side. So as you travel more and more, concentration keep on decreases because of negative sign here. Negative sign is there, no? As you travel more and more, concentration decreases. Understood? This is one question they are asking in the exam. Beyond that, no, one more question they are asking is initial oxygen deficit after mixing. Initial oxygen deficit in river after mixing. After disposing the pollutant is equal to D naught, that is, which is nothing but dissolved oxygen at saturation minus dissolved oxygen of the mix. Dissolved oxygen of the mix, how you can find out? Same way, Q river into DO river plus Q wastewater into DO wastewater by Q river plus Q wastewater. DO sat, DO dissolved oxygen at saturation, that is a constant, depends on temperature, external temperature. So that they will give you. So initial oxygen deficit, one time this question has been asked in GATE exam. Find initial oxygen deficit after mixing sewage effluents into water course having so and so DO, something like that. So you can work out like this. So this question also asked. That's all, that is disposal. Then coming to solid waste management. Solid waste management, more of general type questions they are asking. Graduate aptitude questions. One is 100 by specific gravity of municipal solid waste they are asking. The percentage of component ones. Municipal solid waste is a heterogeneous mixture of so many number of things. So many components are present in solid waste. So if you take their specific gravities and using this expression you can find out. Sometimes they will ask you density of municipal solid waste. Density of municipal solid waste is equal to percentage of component 1 by density of component 1, percentage of component 2 by density of component 2, and so on. This is one question they are asking. Then the second question is energy content. They are asking energy as discarded. Formula is there. It is sigma Pi into energy of individual components by 100. Pi is equal to percentage of ith component present in MSW. Like that, many components are present. Ei is energy content of ith component. So without making any change, you find out energy, that is Ei. Energy as discarded. Energy on dry basis, when you are asked to work out, energy on dry basis is equal to, it is energy as discarded, total energy as discarded, into 100 by 100 minus percentage moisture content, or energy on ash free dry basis. Ash also if you remove, then ash free dry basis you work out, then ash content also have to deduct. So energy as discarded into 100 by 100 minus percentage moisture content minus percentage ash content. This also they are asking questions on energy, questions on specific gravity of MSW. Then how much amount of oxygen is required. So Ca, Hb, Oc, Nd are the composition of municipal solid waste. They will give you like this. A, B, C, D, some numericals they will give. Composition of MSW that react with some components of oxygen and produce carbon dioxide. produce H2O, produce ammonia and something like that. Question will be there. Then how much amount of oxygen is required? Then you will find out. So how much amount of air required, how much oxygen required, how much air required, etc. they are asking. To decompose completely. In that case you have to find out this X value. Then you have to link between, find molecular weight of Ca, Hb, Oc, Nd, find molecular weight of XO2, then you can find out oxygen requirement. So oxygen requirement you get, then you can find out air requirement. So air required is equal to, is oxygen required by percentage of oxygen in air. If you divide, you can get air required. Then density of air will be given, which is equal to mass of air by volume of air. Then you can find out how much air we require. So volume of air required is equal to, it is mass of air required by density of air, that will give volume of air required. Because air is calculated in volumes, so MSW, so and so tons of MSW produce how much amount of air required for given so and so tons of MSW, in so and so tons will give. So and so tons of air will get, that you convert into volume finally. So this question also nowadays they are asking in GATE exam. Okay. In addition to that, one more topic in solid waste management is landfills. So area of landfill, volume of landfill. So landfill design they are asking. Landfill design is nothing but finding area of landfill. For that what we do is total weight of MSW generated, municipal solid waste generated, is equal to, it is rate of generation into population of that city, community for which it is to be designed into number of days for which the system is to be designed. Then it will give you density of MSW, compacted density will give, sometimes uncompacted will give. If compacted density is given to you, then compacted volume of solid waste we can find out. Compacted volume of MSW will get. If uncompacted density is given, then uncompacted volume of MSW will get. Generally compacted volume we calculate. Okay. So if you know density of compacted solid waste, then volume of compacted MSW is equal to, so total weight of MSW generated by density of compacted. This will get so and so meter cube. Then depth of volume of compacted MSW is equal to, suppose that landfill is completely packed to the top. Landfill is packed to top, then in that case volume of landfill is equal to volume of compacted solid waste in landfill. And MSW in landfill. Okay? Then volume is known to you, then depth of landfill will be given to you, then you can find out area of landfill. That is what is called design. Area of landfill is equal to volume of landfill by depth of landfill. So using common sense you can work out. You don't require much engineering for this. This is how we can design landfills. Then last topic is air pollution. In air pollution, first question is concentration of air contaminants changing from microgram per meter cube to air contaminants converting from concentration of air contaminant in microgram per meter cube is equal to concentration of air contaminant given in ppm. It is given in ppm, we are asked to convert into microgram per meter cube or ppm to microgram per meter cube. Either way you can work out. In ppm into, just multiply this by m by k into 10 cube. That's all you will get in ppm. Okay, this M is equal to molecular weight of gas contaminant. Either it is carbon monoxide, sulfur dioxide, carbon dioxide, whatever it may be. And K is a constant whose value is taken as 82.05 into 10 power minus 3 into T by P, where T is equal to temperature in degree Kelvin, P is equal to pressure in atmosphere. So using this expression you can find out, or otherwise if R value is given, R value is universal gas constant, then you multiply this value with K, where R is equal to universal gas constant. Its value, R value is normally 82.05 into 10 power minus 6. 82.05 into 10 power minus 6 is the R value. Its unit says atmosphere meter cube by mole Kelvin. This is R value. So R value is given, well and good, otherwise also no problem. Sometimes the ppm to ppb also will give. If it is given concentration of air contaminant in ppb is equal to, if it is given in ppb, concentration of air contaminant in ppb into just m by k, then we get microgram per meter cube straight away. This is one question they are asking. Then second question is the high volume air sampler, that is total suspended particulate matter present in gaseous state. SPM, suspended particulate matter, or total suspended particulates is equal to W final weight minus W initial weight by volume of air sampled using high volume sampler. So it will get answer in microgram per meter cube. SPM is suspended particulate matter. Suspended particulate matter or total suspended particulates. TSP means total suspended particulates. WF is final weight of filter paper. WI is initial weight of filter paper. So high volume air sampler, it uses filter paper. We measure its final weight of filter paper after sampling. Before sampling also we measure initial weight of filter paper. Okay, and V is equal to volume of air sampled. Volume of air sampled. This volume of air sampled is equal to, it is average airflow rate or airflow rate. Pump is used to suck air, so airflow rate of the pump into duration of sampling you take, then you get volume of air sampled. Understood now? This one question they are asking related to high volume air sampler. In addition to that, so many questions they are asking, but most of them are aptitude kind of question. Sulfur dioxide emission they are asking. Sulfur dioxide emission from thermal power station. So for the finding sulfur dioxide emission, first of all what we work out? Sulfur emission we work out. First we find out sulfur emission. By burning coal we get sulfur. Emission rate of sulfur. Emission rate of sulfur we find out. Then sulfur dioxide easily you can get. Sulfur emission rate of sulfur is equal to, find out emission rate of sulfur. At what rate sulfur is emitted is equal to rate of coal burning. So if you burn coal, then only you will get sulfur into percentage sulfur in coal. Right? You multiply percentage sulfur in coal, you will get this is how much amount of sulfur emission is there. Right? Then sulfur react with oxygen and produce sulfur dioxide. Therefore, one part of sulfur is equal to 2 parts of sulfur dioxide, because molecular weight of sulfur is 32, molecular weight of SO2 is 64. 32 parts of sulfur is equal to 64 parts of sulfur dioxide. Therefore, if we know emission rate of sulfur, then sulfur dioxide emission rate is equal to 2 times emission rate of sulfur. This is one question also they are asking in exam. Okay. In addition to that, control equipment design also they are asking. Electrostatic precipitators. Efficiency formula, based on efficiency formula we can design. It is 1 minus e power minus WA by Q into 100. In this formula, W is drift velocity in meter per second, drift velocity of particle in meter per second, and A is equal to area of plates or area of cylinder. Cylindrical ESP means cylinder area we take. If it is plate, parallel plate ESP means area of plates we take. In meter square this is. Then Q is equal to airflow rate. Rate of airflow in meter cube per second. From this you can design electrostatic precipitator. Okay. Then fabric filters design is same as number of bags required. Number of bags required, they are asking that question. Number of fabric filter bags required. They are asking. This is designed exactly same as design of filter. Total area of filter bags required is equal to, it is Q by velocity of flow. It is airflow rate by velocity of flow, velocity of air. So that will give total area of filter bags required. Then area of each bag is equal to, it is pi d into L. D is diameter of bag. L is equal to length of bag. So circumference only it flow. Therefore, number of bags required is equal to total area of filter bags required by area of each bag. So that will give number of bags. So this kind of questions they are asking. N value you can find. That's all. This is quick revision. I wrote all formulae which we worked out numericals during our 60 hours we revised. Actual content is 120 hours. Total subject you can learn in completely, you can learn every point in 120 hours. But we cut short to half because we focus only on numericals. 60 hours we discussed theory. Then all that 60 hours, whatever numericals we have solved, the related formula we completed in 4 hours. So 120 hour course, actually 120 hours course this is. 120 hours it will take to learn EE course completely, E to learn. Then in revision class, we focused on numericals. We discussed numericals with little small concepts and we reduced that to 60 hours. Then now in a quick revision class, right, all that 60-hour numericals, all formulae related to because GATE is more of numericals, right? We revise in 4 hours. So is it good? Because we don't have time, otherwise we have completed 60-hour class, again I would have converted into some 10 hours class, again quick revision, some 2 hours class, something like that. Anyway, something is better than nothing. So, completed this topic, maybe I will start hydrology next. Okay, let us see. Wish you all the best. Okay, thank you. Unacademy offering 23% discount. So free enrollment or mock exams.